All right, strap in, everyone. Today, we're going deep, really deep,
Yeah, deep into the quantum realm.
into a question that's got philosophers scratching their heads.
Physicists, too.
We've got a whole pile of sources here, all about identity and individuality in quantum mechanics.
Can those tiny particles that make up everything, actually be individuals? Like you and me?
Yeah.
Or are they something else?
That's what we're diving into today, the mind-bending world of quantum objects and whether they even exist in the way we usually think about things.
It's going to challenge how we think about the world.
Big time. I mean, think about it. In our everyday experience, we're surrounded by distinct objects, right?
Trees, books,
You
cats.
can tell your cat from your couch, hopefully.
Hopefully. And there's this philosophical principle, the principle of identity of indiscernibles.
Oh, yeah, I've heard of that one.
It basically says if you can't find any difference between two things, they're actually the same thing.
Makes sense on the surface.
Right. Yeah, at first glance. But then zoom into the quantum level and things get kind of fuzzy.
Fuzzy is an understatement. Because in quantum mechanics, particles like electrons and protons, they're considered indistinguishable.
But indistinguishable in a much stronger sense.
It's not just that they look alike.
It's that no measurement can tell them apart, even in theory.
Well, hold on. Even in theory. Like, we couldn't devise an experiment that could tell them apart.
Nope. Not even with the fanciest tech we could dream up.
So it's like, imagine two red balls, exactly the same. Size, weight, shade of red. You get it.
Identical twins of the red ball world.
Right. But you could still track their paths in
Wow.
principle. Like, this ball went here, that one went there.
You got it, but with quantum particles, you can't even do that.
No way. So even if they swap places, we'd be none the wiser.
Exactly. It's like they don't have that unique fingerprint that we're so used to with everyday objects.
That's wild. So some physicists and philosophers are saying, wait a minute.
They're saying maybe these quantum objects aren't individuals at all?
Okay, let's unpack that. What else could they be, if not individuals?
Well, there's some fascinating ideas out there.
Like what?
Some folks are suggesting they might be what we call intentional-like entities, defined more by their purpose, their role in a system.
So like, a hammer is a hammer because of what it does, not just what it's made of.
That's one way to think about it.
Intriguing.
Mm-hmm.
So we should think about an electron's function within the whole quantum system, rather than as a tiny independent thing.
It's a shift in perspective, for sure.
And is that the only alternative?
Oh, no, there's more. Another idea is that they're part of these strange collections called quasets.
Quasets, what in the world are those?
They don't behave like normal sets, that's for sure.
Okay, now I'm really intrigued. So these quasets, they challenge how we think about grouping things together.
Big time. They challenge some really fundamental assumptions.
Whoa, okay, so we're talking about a fundamental challenge to the very idea of an object being itself.
Like an electron not even being an electron in the way we usually think about it.
My head is starting to spin.
It's mind-bending stuff. It's like our whole understanding of what it means to exist is being shaken up.
Before we fall down the quantum rabbit hole, though, do all physicists and philosophers agree with this non-individuality idea? Or are there other perspectives?
Oh, absolutely. Plenty of folks are trying to reconcile quantum weirdness with the idea of individuality.
They're not ready to give up on the idea of individual things just yet?
Not quite.
So how are they trying to make sense of it all? What are some of their explanations?
Well, one approach they're taking is called weak discernibility.
Weak discernibility.
It's a mouthful, I know.
So instead of focusing on the particles like internal properties,
They look at relationships.
relationships. How do you distinguish two things that are supposed to be identical through their relationships?
Think of it like two dancers, right? Perfect mirror images of each other.
Okay,
Same clothes, same moves. You can't tell them apart just by looking.
I'm with you so far.
But you can tell them apart by how they relate to each other, right?
Oh, I see. Like one always leads, the other follows.
Exactly. Or they might always be like facing each other or something.
So you can't say this is dancer A and this is dancer B for sure.
Right, right.
But you can still identify them as individuals based on that consistent pattern of interaction.
You got it. And that same logic can apply to quantum particles.
Okay.
Even though we can't pinpoint their individual properties,
Right.
we can observe how they relate to each other.
Give me an example.
Their spins might always be opposite,
Ah.
or they might always be found in a certain configuration.
So their connection is what makes them individuals, even though we can't actually tell them apart otherwise?
It's a way to make sense of it, yeah.
TV.
But not everyone buys into this, of course.
And of course not. It's quantum mechanics. Nothing's easy.
Right. There's another approach, sometimes called the heterodox approach.
Heterodox. What's that one all about?
They argue that the problem isn't with the particles themselves,
Oh,
it's with our language
our language, like the words we use.
and how we try to label them. Yeah.
So they're saying the particles are discernible.
Kinda, yeah. They argue that the labels we use in our mathematical descriptions,
Right.
they don't actually refer to specific particles.
Even though we often talk as if they do.
Exactly. It's a bit like,
Go on.
think about those identical twins again.
Oh, right, the dancers from before.
You can tell there's a difference between them. Right.
Well, yeah, they're two separate people.
But you can't just point and say, this is twin A and this is twin B for sure.
It's true, true.
It's not that they're indistinguishable.
But our language, our labeling system, can't quite capture it.
You got it.
So they're not saying we can't distinguish the particles at all,
Right.
but that our current way of talking about them is limiting.
Precisely. This view suggests there is a difference,
Okay.
but we just haven't figured out the right way to express it yet.
The right way to express it.
In a way that fits into our current scientific framework. I mean,
That's a brain twister. So are we any closer to answering the question then? Are these quantum objects individuals or not?
well, that's where things get even more interesting.
Well, boy, I'm almost afraid to ask.
The physics itself doesn't actually give us a clear answer.
No.
It's what's called metaphysical underdetermination.
Metaphysical underdetermination. Now that's a mouthful. What does that even mean?
It means different interpretations of the same physical phenomena.
Okay.
Like the indistinguishability of these particles can lead to totally different pictures of reality.
Whoa, so we've got all these different interpretations, each with its own set of assumptions and what they mean.
And they're all consistent with the same physical data.
So how do we choose? How do we know which one is right?
That's the million-dollar question. It brings up this whole debate between realism and anti-realism in the philosophy of science.
Okay, hold on. Break that down for me and for our listener who might not have a PhD in philosophy.
Sure, sure. Realism basically means the world exists independently of our minds, and our scientific theories are getting closer and closer to describing that objective reality.
So the realists think there's a truth out there, and we're slowly uncovering it through science.
Yep. Anti-realism is a bit more cautious.
Cautious how?
It suggests that our theories are just useful tools, for predicting and explaining the world.
But they don't necessarily tell us how things really are.
Exactly. An anti-realist might say that all these different interpretations of quantum mechanics are equally valid.
Because they're just different ways of looking at the same thing.
Different models of the same observable phenomena.
And quantum mechanics, with all its weirdness, kind of throws a wrench into this whole debate.
It really does.
Because if we can have all these different contradictory descriptions of the same reality,
Yeah.
what does that say about our ability to really know the world as it is?
Oh, that's a philosophical conundrum. Can science really tell us what reality is? Or just how it behaves from our limited point of view?
Man, this is heavy stuff. My brain's doing quantum leaps of its own right now.
We've gone pretty deep down the rabbit hole, haven't we? But there's another path we could explore.
Oh? What's that?
One that tries to move beyond this whole idea of objects altogether.
Beyond objects. Okay, now I'm really curious. What does that even mean?
Some folks are saying, yeah, instead of asking if quantum objects are individuals, we need a whole new way of thinking about reality.
A whole new way of thinking. That's a pretty big claim. Instead of objects, what else is there?
Well, they're saying, what if instead of individual particles being the, fundamental building blocks,
Right.
we focus on the relationships, the patterns that connect everything? It's like switching from a close-up to a wide-angle lens.
Okay, I'm trying to wrap my head around that. What does that even look like, thinking about the world in terms of patterns instead of objects?
Imagine like a school of fish, right?
Yeah.
Each fish is doing its own thing, moving around.
But they're all moving together.
But there's also this bigger pattern, right? The whole school swirling together.
So the focus shifts from the individual fish to the whole school, to the pattern.
Exactly. The pattern itself has its own kind of coherence, even though the individual fish are constantly changing positions.
Okay, I'm kind of seeing it. And that's where these fields come in, right?
Right. In physics, a field is basically a region of space where every point has a certain value.
Okay, but how does that apply to, like, Electrons and protons.
Well, in quantum field theory, particles aren't seen as these independent little things.
Oh.
They're more like disturbances, excitations in these underlying fields.
Disturbances.
Yeah, like a ripple in a pond.
Ooh, I like that analogy.
The ripple isn't a separate thing from the pond itself, it's just a temporary pattern within the pond.
So instead of picturing an electron as a tiny ball bouncing around.
It's more like this fleeting pattern of energy in this massive quantum field.
Wow, that is a much different way of thinking about it. So then the question of whether these excitations or whatever are individuals, it kind of doesn't even matter anymore.
Exactly. It's like asking if a wave is an individual. It's just a temporary expression of the ocean.
Whoa. So the focus shifts to the field itself, this interconnected, dynamic thing that's behind everything. It's starting to sound kind of like the Force.
Yeah. Not a bad analogy.
Okay, but real talk. What does this all mean for, like, the average person? Should I be thinking of myself as a ripple in a giant cosmic pond?
Well, maybe not that literally, but I think it highlights how interconnected everything really is.
Even more than we usually think.
Yeah, even the things that seem totally solid, your chair, my desk, that coffee mug over there.
Right, yeah.
Ultimately, they're made up of these quantum objects that are doing all this crazy stuff we can barely even wrap our heads around.
The world is stranger than we can imagine. No wonder this stuff keeps philosophers up at night.
It really is. But it's a good kind of strangeness. It's an invitation to explore more, you know? There's so much we still don't know, and what we think we know. Well, it's probably just the tip of the iceberg.
You've definitely given everyone a lot to think about today. Before we wrap up, is there anything else you want to leave our listeners with? What's the one big takeaway you hope they remember?
I'd say don't be afraid to question what you think you know about the world.
Yeah, good advice.
Quantum mechanics shows us that reality is way more complex than we usually assume.
It's like a constant challenge to expand our understanding.
Exactly.
Well, on that note, I think we'll wrap up this deep dive into the wild world of quantum individuality, non-individuality. Who knows? Maybe by next time we'll have a whole different answer.
Haha, maybe. Keep those brains buzzing till then.
Thanks for listening, everyone.